Our planet is a marvel, a blue oasis in the vast cosmic ocean. It teems with life, protected by an invisible shield, Earth's magnetic field. This magnetic bubble, generated deep within our planet's core, acts as a guardian against harmful radiation from the sun and cosmos. But this shield is not static. It's a dynamic force, constantly shifting and changing over time. Imagine a giant bar magnet inside our planet, tilted slightly off-axis. That's a simplified picture of our magnetic field. Its magnetic lines stretch far out into space, forming a protective cocoon around Earth. This cocoon deflects most of the sun's charged particles, known as the solar wind, keeping our atmosphere from being stripped away. So let's delve deeper into the heart of our planet and unravel the secrets of Earth's enigmatic magnetic field. Deep beneath our feet, about 1,800 miles down, lies Earth's core. It's a place of immense pressure and unimaginable heat, hotter than the surface of the sun. This core is not some solid mass. It's a dynamic region divided into two layers, a solid inner core and a liquid outer core. This liquid outer core is where the magic happens. This liquid iron, kept in constant motion by Earth's rotation and internal heat, generates electric currents. These currents, in turn, create a magnetic field, a phenomenon known as the geodynamo. Think of it like a giant self-sustaining dynamo, constantly generating the magnetic field that envelops our planet. But here's the catch. This dynamo isn't perfectly stable. The flow of iron in the outer core is turbulent and chaotic, causing fluctuations in the magnetic field. The magnetic North Pole, the point on Earth where a compass needle points down, is not static. For centuries, sailors and explorers have relied on the compass as their guide, its needle faithfully pointing towards magnetic north. But there's a secret that every seasoned navigator knows. Magnetic north and true north are not the same. True north, also known as geographic north, is the fixed point where all lines of longitude converge at the North Pole. Magnetic north, on the other hand, is the point where Earth's magnetic field lines vertically downwards. It's the direction that a compass needle points to, and it's not fixed. The difference between magnetic and true north is called magnetic declination. It varies depending on your location on Earth and, importantly, on the whims of our planet's ever-changing magnetic field. For most casual navigation, this difference might seem negligible. But for high-precision navigation, like that used by ships, aircraft, and even some smartphones, accounting for magnetic declination is crucial. With the magnetic North Pole constantly on the move, navigation systems need regular updates to ensure accuracy. At the top and bottom of our world, where the icy landscapes meet the sky, navigation becomes an entirely different beast. The poles are where Earth's magnetic field lines converge, plunging down into the planet. And it's here, in these extreme environments, that the impact of Earth's shifting magnetic field on navigation is most acutely felt. Near the poles, compasses become unreliable, their needles swinging erratically as they struggle to find a stable magnetic field line. The familiar grid of latitude and longitude, so crucial for navigation elsewhere on Earth, becomes distorted and less useful. GPS, which uses satellites for positioning, has become an indispensable tool in these regions, providing a reliable alternative to traditional magnetic compasses. However, even GPS isn't immune to the quirks of our planet's magnetic field. The ionosphere, a layer of Earth's atmosphere that's ionized by solar radiation, can interfere with GPS signals, particularly in the polar regions where the magnetic field lines dip closer to the surface. Earth's magnetic field is more than just a navigational aid. It's a fundamental part of our planet's life support system. It acts as a shield, protecting us from the constant bombardment of charged particles from the sun and beyond. This stream of charged particles, known as the solar wind, would be devastating to life on Earth were it not for our magnetic field. When these charged particles from the sun collide with Earth's magnetic field, they get trapped in the magnetosphere, the region of space dominated by Earth's magnetic field. This interaction creates stunning auroras, those shimmering curtains of light that dance across the polar skies. But it also highlights the protective role of our magnetic field, deflecting the brunt of the solar wind and preventing it from stripping away our atmosphere. Without a magnetic field, Earth would be a very different place. Our atmosphere would be thinner, exposed to the harsh radiation of space. The oceans, no longer protected, might evaporate. The magnetic field's influence is not limited to deflecting solar wind. The human body is a complex electrical system. Our nervous system relies on electrical impulses to transmit signals throughout the body. Our heart, the engine of life, beats to the rhythm of electrical signals. So it's not unreasonable to wonder if external magnetic fields, like those generated by Earth and various technologies, might have some effect on our health. Some studies have suggested a possible link between extremely low-frequency magnetic fields, ELF EMFs, like those emitted by power lines and electrical appliances, and an increased risk of certain health problems, including childhood leukemia. However, the scientific evidence is far from conclusive, and many other studies have found no such link. The World Health Organization, WHO, states that current evidence does not confirm the existence of any health consequences from exposure to low-level electromagnetic fields. However, the WHO also acknowledges that more research is needed to fully understand the potential long-term effects of exposure to magnetic fields. One area of active research is the effect of magnetic fields on sleep. Some studies have suggested that exposure to magnetic fields might influence melatonin production, a hormone that regulates our sleep-wake cycle. Humans aren't the only ones who seem to be attuned to Earth's magnetic field. For centuries, people have observed animals navigating with uncanny accuracy, often over vast distances, birds migrating across continents, sea turtles returning to the same beach to lay their eggs, salmon swimming upstream to spawn. These feats of navigation have long puzzled scientists. Increasingly, evidence suggests that some animals possess a magnetic sense, an ability to perceive Earth's magnetic field and use it for navigation. This sense, known as magnetoreception, is thought to be based on specialized cells or structures that contain magnetic particles, allowing animals to sense the direction and intensity of the magnetic field. Birds, for example, are thought to have iron-rich magnetite crystals in their beaks that align with Earth's magnetic field. This alignment is thought to provide birds with a kind of internal compass, allowing them to navigate with remarkable precision, even on cloudy days when the sun and stars are not visible. The study of animal magnetoreception is a fascinating and rapidly developing field. Earth's magnetic field is not a static phenomenon. It's a restless entity, constantly changing over time. Geological records, locked away in ancient rocks, reveal a history of dramatic shifts in Earth's magnetic field, including complete reversals where magnetic north and south swap places. These reversals, known as geomagnetic reversals, are not frequent occurrences. They happen on average every few 100,000 years, though the timing is unpredictable. The last full reversal, known as the Brunhes-Matuyama reversal, occurred about 780,000 years ago. During a geomagnetic reversal, the magnetic field weakens, becomes more complex, and may even disappear entirely for a period. The magnetic poles wander and can even appear at the equator. This process can take thousands of years, and the exact mechanism behind these reversals is still a subject of scientific debate. The prospect of Earth's magnetic field flipping, with north becoming south and south becoming north, might sound like a scene from a science fiction movie, but it's a real phenomenon that's happened many times throughout our planet's history. The question isn't if it will happen again, but when. Scientists can't predict exactly when the next geomagnetic reversal will occur, but the current weakening of Earth's magnetic field and the rapid movement of the magnetic North Pole have sparked speculation that we might be heading towards a reversal in the next few thousand years. So, what would a geomagnetic reversal mean for us? During a reversal, the magnetic field weakens, providing less protection from the sun's radiation and cosmic rays. This could lead to increased radiation exposure at Earth's surface, potentially disrupting satellites, power grids, and communication systems. Some scientists believe that increased radiation exposure during a geomagnetic reversal could have biological impacts, potentially influencing mutation rates and evolution. However, there's no conclusive evidence to suggest that past reversals have caused mass extinctions or posed significant threats to life on Earth. Earth's magnetic field is more than just a scientific curiosity. It's a fundamental aspect of our planet that makes life as we know it possible. Understanding how it works, how it's changing, and how those changes might impact us is crucial for our future. Scientists continue to study Earth's magnetic field using a variety of tools and techniques. Satellites orbiting our planet provide a global view of the magnetic field, tracking its strength and variations over time. Ground-based observatories measure magnetic field fluctuations, adding to our understanding of this dynamic force. By studying the past, present, and future behavior of Earth's magnetic field, we can gain valuable insights into the inner workings of our planet, the risks posed by space weather events, and the potential impacts on our technological infrastructure. This knowledge will be essential for developing strategies to mitigate the potential consequences of future magnetic field changes, ensuring the resilience of our technology and the well-being of life on Earth. From the depths of our planet's core to the vast expanse of space, Earth's magnetic field is a force to be reckoned with. It's a shield, a protector, a guide, and a source of endless fascination. As we delve deeper into its mysteries, we gain a newfound appreciation for the delicate balance of forces that make life on Earth possible. The magnetic field is a reminder that we are part of something much larger than ourselves, a dynamic system that's constantly evolving. Its constant shifts and changes challenge us to adapt, innovate, and deepen our understanding of the universe we inhabit. As we venture further into the cosmos, exploring other planets and seeking signs of life beyond Earth, understanding magnetic fields will be crucial. The presence or absence of a magnetic field can make or break a planet's habitability, influencing its atmosphere, its oceans, and its potential to support life as we know it. So, let us embrace the challenge of unraveling the magnetic mysteries that surround us.